So hello everyone. Today we're going to be looking at another way to measure angles, which is called radians. Radians are used quite a bit in math and science in higher levels. Therefore, it's really important to start seeing them as soon as possible. And this is as good a time as any. We're going to have to warm up a little bit to get there, though. So I want to just get your brain thinking about some examples here related to ratios. So ratios are like percentages, right? If I say a ratio is just a fraction, so 1 out of 2. But 1 out of 2 is a percentage, it's 50%. And what's interesting about ratios and percentages is they can be used and applied to various units, even amongst each other. So for instance, I can say what is for 50% of 1 dozen eggs, or I can say what is 50% of a population. 50% is a percentage or a ratio. It can be put in front of any other unit because itself, it doesn't have a unit. It's just telling us a proportion of the thing that we're talking about, right? So if I ask the question, how many degrees does the second hand go through from the 12 to the 3 on a clock? So all of a sudden we're relating seconds to degrees, but that's not too difficult because we know that if you're going from the 12 to the 3 on the clock, that you're actually going a quarter of the way around the clock. So what does that mean for how many angles you've gone through? Well, on a clock, just move this down a little bit. So on a clock, if I'm going from the 12 to the 3, I've gone 1/4 of the way around the whole clock. And the entire clock is 360 degrees, right? So I can say that 1/4 times 360 degrees is equal to 90 degrees. Now I could also say, what is the arc length or the distance traveled by the minute hand as it sweeps past that arc? What is that distance traveled during the 1/4 turn? Well, we know that the circumference of the entire clock is 2 pi r. So if I'm doing 1/4 of that distance, I would just multiply 1/4 times 2 pi r, and I would get my final answer depending on what r was. Sorry, I wanted to simplify that. So the 2 and the 4 would simplify, so it would be pi r over 2 in circumference, right? But if r is equal to 8, I would get pi times 8 over 2. If pi was equal to 3, if r was equal to 3, I'd get pi times 3 over 2. Whatever your radius is, would then change how big that arc length is. Obviously, the bigger the clock, the more of distance you've traveled in that quarter span. So the question becomes, can we use these concepts that we just talked about to redefine angles using the circumference of a circle instead of degrees? And we're going to use a radius 1 circle, just like we did with the magic circle to start. And as we've seen with the magic circle, you can change the size of the circle later on, and proportionally everything still works. Okay, but we're going to use a radius 1 circle to start. So if I started with half of a circle, I want to define this arc length both in angle and in circumference. Okay? So the angle is easy. The angle is 180 degrees, right? And what we say is 180 degrees, the word we use when an angle is trapped inside of an arc length is subtended. So 180 degrees is the angle subtended. Oops, I always spell that wrong, sorry. It's a D-E-D. Subtended by the arc. So how much of the circle have I done? Yeah, that's a fun word for sure. Um, so I would do 180, and here's my ratio. What am I dividing that by? I'm dividing it by 360 degrees, right? Yeah, chat, I'll get to that. So I'm using the degrees right now. I'm doing 180 divided by 360, and I'm going to multiply that by 2 pi r. But we said that r is equal to 1, right? It's a radius 1 circle. So that becomes 180 divided by 360, which is just 1/2. And I want you to notice that the degree symbols disappear at this point. When you divide centimeters by centimeters, the centimeters disappear. The units cancel out just as much as the numbers do. So degrees divided by degrees, there's no more unit attached to that 1/2. And now I'm just multiplying it by 2 pi instead of by 2 pi r, because r is equal to 1. And that just simplifies to pi. Well, that means that my 180 degree angle can be represented by pi. Pi is the same thing as 180 degrees. It represents the same trajectory around the circle. If I do another circle, I'm just going to draw this one freehand. It might look terrible. Oops. I didn't want that to be green. Whatever. Let's say we do our 90 degree from our previous slide, right? I would do 90 degrees divided by 360 degrees. That's going to give me my ratio times 2 pi r. But again, r is equal to 1. What's 90 divided by 360? That's 1/4 if you simplify it, times 2 pi, the r is equal to 1. And we end up with pi over 2. And what that means is, once again, 90 degrees is kind of replaceable by pi over 2 as an angle measurement, because pi over 2 represents the same amount swept through by the angle, just by the circumference instead. And this leads us to, what if we do the entire circle? What if I go all the way around? Now I have 360 divided by 360 times 2 pi, which gives 1 times 2 pi, which is just 2 pi. And therefore, 360 degrees is equal to 2 pi when we talk about the proportion of the circle that we've gone around. And what that leads us to is, if I divide both sides by 360, and this time I'm not dividing by a degree measure. I'm just getting rid of the 360 by dividing by 360, and that's going to give me 1 degree. If I simplify the 2 and the 360, I end up with pi over 180. And this is actually what we call the conversion from 1 degree to radians. This is what we call our conversion factor. And we're going to talk a little later about the conversion factor to go the other way. What if I want to go from radians to degrees instead of degrees to radians? I can now use this to convert any degree value into its corresponding radian measure. And radians are just, and I'll explain this a little bit more on the next slide, but they're just a way of representing the angles using circumference, parts of the circumference of a circle instead. And that's a very, very useful thing, because when you talk about the circumference of a circle, you're talking about a metric measurement. Degrees aren't metric. Degrees are based off of a Babylonian system that I believe was divisible by 6. All of our numbers are divisible by 10. They're decimal. So if you try to mix degrees with other units, it's very difficult to do. In fact, I don't know if I can think of any real scenario where degrees are mixed with like centimeters. or other units, because it doesn't make any sense. They're not the same base number. But rads are. Radians are metric. So you can actually mix radians with other measurements. In fact, even though I wrote rad here, rad is technically not a unit. Rad is more of a way to remind you to make sure you have the right mode on your calculator. Okay, but you can just write pi over 180. You don't have to write the word rad. You do have to write the unit degree though. Okay, so radians are very, very powerful because of that, and it'll start to make a little bit more sense in the next few slides. But let me just show you an example. If I asked you to convert 30 degrees into rads, what you would do is use that conversion factor. All right, if 1 degree is equal to pi over 180 rads, I would just multiply both sides by 30. 30 times 1 degree is 30 degrees. 30 times pi over 180 can simplify. And we end up with 30 degrees is equal to pi over 6 rads. So pi over 6 is the exact same type of thing as an angle as 30 degrees is. But pi being 3.14, sorry, and the irrational decimal of pi, right? If you push your pi button on your calculator, you just divide that by 6. It'll give you some sort of ugly decimal, but that is a metric measurement, whereas 30 degrees is not metric. In your textbook, they actually have a definition of 1 radian. I don't particularly like this definition. I mean, it's important in math, but it's difficult for students to understand the link between this and what I just showed. So I'm going to put it here in your note. I'm going to talk about it for a second. You can go read up on it on page 330 in your textbook if you really want to. But this is what 1 rad is, okay? If you take any circle, create an arc length between 2 radiuses of the circle. So this angle is subtended by that arc length. If that arc length is equal to the radius, this angle is 1 rad. That's the actual definition for a radian. So if your arc length is equal to the radius of the circle, the angle that's subtended by that arc length is 1 rad. The problem is I don't find that very useful in conversions or anything like that, but that is the definition of a radian. Okay, so take it for what it is. I'm going to put it in your note, and you can go read up on it more if you'd like. Okay? All right. What I want to do next is I want to show you what happens if you calculate the length of an arc. So I want to calculate the length of this arc. This arc is subtended, or the angle 60 degrees is subtended by that arc length, okay? I want to do it in degrees to start, and something really cool is going to happen when I finish, all right? So, how would I calculate it using degrees? Well, how much of the circle have we covered by only opening this pi shape up by 60 degrees? Well, it's a ratio. It's 60 degrees divided by 360 degrees. And we're going to do this now for any type of radius, so not just a radius 1. Okay? So what is 60 divided by 360? That is 1/6 times 2 pi r. And that is equal to, if we simplify it, pi over 3 times r, which I'm actually going to write as r times pi over 3. Okay, you'll see why in a minute. Now this is interesting. We started with degree values, but all of a sudden it looks like we have radian measures in there. And if we convert 60 degrees into rads, using the conversion factor that I showed on the previous slide. So we know that 1 degree is equal to pi over 180 radians. I've got to be very careful here, folks. I kept stumbling over my words in the previous lesson. Radians and radius are very, very similar words. And I mean, they're supposed to be, because the rad is defined by the radius of the circle, okay? But this is radians, not radiuses. So I'll try to be as clear as I can when I say that. Anyway, we're going to convert 60 degrees into rads, all right? So I'm going to multiply both sides by 60. So that, oops, this is supposed to be 1 degree, not 10. Sorry about that. So we end up with 60 degrees is equal to pi over 3, if I simplify that. 60 and 180 simplify to pi over 3. But wait a second. We ended up with a pi over 3 over here. 60 degrees converts to pi over 3. Doesn't that therefore mean that the arc length, the most efficient way to calculate it, would be to take the radius and multiply it by an angle, but that angle should be in radians? I mean, look at how much simpler it is. If your angle is already given to you in radians, all you have to do is take your radius and multiply it by that value, and you'll get the exact same thing we did when we had to do all of this jibber-jabber stuff up here. And the arc length formula is actually defined that way in mathematics textbooks. And what's beautiful about this is I don't have to worry about that degree centimeter problem that I was talking about earlier. There isn't going to be a mixture of two different units here anymore. Okay? Because if I had started with, like, notice here, when I started with degrees, the degrees canceled out because they were dividing each other. They had to, because I can't end up with degree centimeters. Radius would be measured in meters or centimeters, right? I can't end up with that kind of a mixture of units. But if I start with radians to begin with, I don't have to worry about that, because the radians are unitless. You can measure, you can multiply centimeters times radians because it gives you centimeters as an answer. For instance, if my radius was equal to 5 centimeters, my arc length would be 5 times, and in this case it was 60 degrees, which is pi over 3, and that would just be 5 pi over 3 centimeters. And it all works out. I'll always remember sitting in a university class. This was my, I think it was 3rd or 4th year university. This is how long it took for this to sink in my brain. I think it was 3rd or 4th year university, and I was doing a question on angular velocity, which is actually some questions that are in your textbook. And angular velocity is the speed at which something is spinning, okay? And the letter that we use is omega for that variable. And I did the question in degrees, and I got an answer, and my prof looked at my answer and said, "What are you doing working in degrees? We're physicists. You should know better than that. We work in radians. We don't work in degrees." That's the way he talked to me about that. Okay? And I still remember it to this day. And I mean, he had a right to be upset. I should have known by that time. I don't know why it didn't sink in, but it didn't. I must have just forgotten. I hadn't worked in angular velocity in a while. But he was visibly upset that I was using degrees in that question. And it's because we are so used to using degrees, we're obviously going to switch over to degrees if we forget that radians are actually the better measure. They are much more useful than degrees. Okay? Degrees are easier to learn as students are learning math from a younger age, obviously. But radians are a much, much, much better angle measurement than degrees are. Not sure if I'm convincing you yet. Okay. That leads us to this. Dun, dun, dun. I found this today on the internet. I was so happy that I did. If there's any diagram that's going to be important for a lot of you, if you continue on in IB math or continue on in science, specifically physics or math at the university level, you're probably going to need to memorize this picture. Now, there are patterns to help you memorize it. We've already seen some of those patterns. Specifically, the 1, 2, 3, 1, 2, 3 pattern right here. 1, 2, 3, 1, 2, 3 to get my three special angles and their cosine and sine values. So just a reminder that all the x coordinates are the cosine values, all the y coordinates are the sine values, right, of those points. But it also tells you the angles in both degrees and radians for each one of those. Okay? And if you know this first quadrant, you can then develop everything else in every other quadrant because it's just mirror images of those. But one thing I want to go over, actually there's two things I want to go over with you. I want to show you on a calculator how you would get root 3 over 2 using 30 degrees or using pi over 6. And I just want to make sure you see it at least once. Some of you may already know how this works, but I want to make absolutely sure. So I'm going to try to do something here. I'm hoping you'll be able to see both my calculator and the page at the same time. So I believe that has worked. Let me just clear this out from the previous lesson here. Okay, so, oops, I wanted to delete that. There we go. Let's say we do regular cosine 30. Now we know that cosine 30 is root 3 over 2 because it's that value right there, right? If I do cosine 30 on my calculator, this calculator works backwards. I have to put the numbers in first and then press cosine. I get 0.8660. I don't know if some of you are starting to memorize that root 3 over 2 is 0.8660. But you're going to see that decimal a lot when you're doing, cosine 30 or sine 60. Both of those give the same thing. How would I get 0.8660 with pi over 6 instead? So somebody just asked in chat, where did I get this picture? I will be posting this note to the classroom stream. But if you like, I can post it as a separate document. I can do that. I think I have it as a Word document somewhere else anyway. So I can do both if you would like. And that's a good question because it is a very, very important picture. Whoops. Let me bring back my calculator. Okay. So pi over 6, I want to use that as my angle instead. Well, this is what you have to do. On every scientific calculator, there's a way to change the mode of the calculator from degrees to radians, and then the third one to gradians, which we rarely ever use. So this calculator, I just press the DEG button, and it goes to rad. The button you're probably looking for on your calculator is the DRG button. DRG stands for degrees, radians, gradians. Okay? So if I wanted to do pi over 6, all right, I would do pi, and I do not recommend you use 3.14 ever anymore, by the way, unless you're just trying to estimate something in your head. You should always use the pi button because it stores many more significant digits than your brain or 3.14 can, okay? So pi divided by 6 is going to give me this 0.52. I'm in rads. If I now do the cosine of 0.52, it's going to give me 0.8660, which is root 3 over 2 again. So I cannot stress this enough, folks. I'm not sure how important it'll be this year because we're not going to necessarily be in an exam situation this year. But in grade 12, if you're doing a trig unit in grade 12, there are going to be some questions that are going to be in degrees and some questions that are going to be in radians. You have to be very aware of which mode your calculator is supposed to be in. because if you do not put your calculator in the right mode, every question you did in the wrong mode is going to be wrong. All right? So it's very, very important that you know where your button is to switch the mode of your calculator over when you need to. And you have to be super aware when you're reading a word question or a trig question in math, specifically trig, or science. It can happen in science as well. Are you in rads or are you in degrees? And switch your calculator to the correct mode. Okay? And as long as it's in the correct mode, it will work. So chat just mentioned that it's been done by accident before already. And it may be that, if your calculator's in your school bag, it might get pressed. The buttons might get pressed in your school bag. And, I mean, it's a button like the other. It'll switch the mode on your calculator, and all of a sudden you don't even realize it's in the wrong mode. So as a teacher, I always try to remind students, make sure your calculator is in the right mode before you start any kind of test or exam. But I'm trying to drill it in now. I hope you understand why, because it's an important lesson to learn. Okay, so that's the first thing I wanted to show. I'm going to go back to my other way of displaying this slide here. Here's the next thing I wanted to show. How could you help yourself memorize this picture? Well, let's talk about some of the patterns besides the one that I just showed. Okay? Now I'm going to show a really simple one in degrees. If you start with 30 degrees right here, if we keep adding 30 degrees, we're going to hit most of the rest of the special angles. 30 plus 30 is 60, plus 30 is 90, plus 30 is 120, plus 30 is 150, plus 30 is 180, blah, 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 all the way around the circle. Okay? Here's a small little activity that I think anybody who is continuing on in math should do. And do it on a, regular basis, maybe even just today. Count up by pi over 6. Pi over 6 is the very first angle. If we count up by pi over 6, what's the next one added to it what's the answer that I get when I add pi over 6 to pi over 6? Isn't that 2 pi over 6? But simplify that in your head. What's 2 pi over 6 simplified? That's pi over 3. Well, here's that angle. What's 3 pi over 6? So we did 1 pi over 6, 2 pi over 6, 3 pi over 6 is pi over 2. Well, what's that angle? And the next one would be 4 pi over 6, which simplifies to 2 pi over 3. What's that angle? Okay? And then 5 pi over 6, which doesn't simplify. So if you count up by pi over 6s all the way around the circle and keep adding 30 degrees to that number, just as an exercise to start memorizing this, at least the first and second quadrant, I would say, for this year, it's going to help you enormously in the future. Now, the problem is we skipped over pi over 4, right? But pi over 4 is its own starting point because that's 45 degrees. You can't add 30 to get to 45 from 30, right? But what if we count up pi over 4 and then 2 pi over 4? What does 2 pi over 4 simplify to? It simplifies to pi over 2, which is 90 degrees. 3 pi over 4 is the next one. That one doesn't simplify, but what angle is it? It's 3 times 45 degrees, which is 135. And just keep doing that until you start to really memorize pi over 6, pi over 4, pi over 3, pi over 2. Like those first 4 in the circle here. And it's a little bit confusing because the denominators get smaller as you get to the top, and the denominators don't technically follow a pattern, right? So I get some students that try to figure that out. Although this was 4, 3, 2, so that kind of does follow a pattern, but it starts with 6. So 6, 4, 3, 2, you might want to memorize that. I don't know. But pi over 6, I always think that the smallest angle, 30 degrees, has to have the biggest denominator because you're dividing 180 by 6 to get 30. If you go back to that conversion I showed earlier, speaking of conversions, what if I threw at you, now you can see it right on the circle here, but what if I asked you to convert 5 pi over 3 into degrees? Let's talk about that conversion because we haven't done that yet. You already know that 1 degree is equal to pi over 180. If you go back in slides, that's the conversion factor, right, for degrees to rads. What if I wanted to reverse that? Well, if I wanted to reverse that, I'd want to get the 1 on this side. How would I get a 1 on this side of the formula, of the conversion factor? Well, I'd take the 180 and I'd move it over to the other side, and it would multiply to the 1 degree, so it becomes 180 degrees. I take the pi and I divide it over to this side, and what's left on this side is 1 rad. So basically, just taking the reciprocal of the conversion factor, pi over 180 becomes 180 over pi, is how you find the conversion factor for rads to degrees. If I take 5 pi over 3 now, and multiply it by 180 over pi, 180 degrees, sorry, over pi, the pi's are going to cancel out. 180 divided by 3 is 60. 60 times 5 is 300 degrees. And I've now converted a radian measure into an angle degrees if I have to do that. Okay, I believe this is the last slide. So I wanted to end today with showing you where this could actually come into play. Okay, there's going to be other examples in your homework tonight, but you could now see a question like this. Pi over 4, the angle is given in radians, so I'd want to make sure my calculator is set to radians. Now, there's going to be 2 ways of answering this question. We could find the exact answer, or we could find the decimal answer, all right? And I'll talk about those 2 in a second. But before I do that, here's a quick challenge. If I only ask you to find this side length, why is that sufficient to solve the entire triangle here? In other words, why do I not need you to find that side length in this case and still be able to solve the triangle? Anybody chat? What angle is pi over 4? Oh, you guys just made the same chat thing that happened in the previous lesson. Somebody said 45 and somebody said 60. Exactly the same thing that happened in the previous lesson. That's amazing. One of those 2 people is right. What is pi over 4? Well, if I multiply pi over 4 times 180 over pi, and you know what? Don't worry about making mistakes here, right? Sometimes making mistakes is going to be the way that you remember to never make the mistake again, right? And it's easy because we just saw pi over 3, pi over 4, pi over 6, right? Which one is which? But 180 divided by 4 is 45 degrees. If this angle is 45, folks, what kind of triangle is this? And if it's an isosceles triangle, what's special about the two sides? Right? So if you see a pi over 4 corner, that is now an isosceles triangle if it's a right angle triangle. So those two sides, exactly, chat, they'll be the same. So all I need to do is find that one side length. All right? So it's getting used to the idea that there's a new way of writing 45 degrees. And that is pi over 4. All right? So let's find the solution to this side length. If I do sine of pi over 4, that is equal to the opposite, which is the side length I'm looking for, divided by the hypotenuse. Now, that means that x, let's isolate x on the left, x would equal to 14 times sine pi over 4. I hope you all agree with that. Let me put brackets around the pi over 4 here to make sure you know that it's all in one thing. Okay? Now, if you wanted to type that into your calculator, you would set your calculator to radians. I'm just going to do this off to the side. If you have a calculator, you can try it with me. My calculator is already in radians, so I'm going to do pi, which is 3.14, blah, 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 right? I'm just pressing the pi button, divided by 4. And then I'm going to sine that. And that gives me 0.7071. And that answer will be, and I haven't rounded it off yet because I'm just going to keep that whole answer in memory and multiply it by 14. And I'm getting approximately 9.899, which I could round off to 9.9. Okay, and it would be centimeters because the units are in centimeters, right? Now that is an estimated answer. Because I rounded it off. But what if I asked you for the perfect or exact answer? When you do 14 times sine of pi over 4, did anybody, I'm wondering, because I've mentioned this number before here, folks, what fraction is 0.7071 on our magic circle? What is sine and cos of 45 degrees, or pi over 4, on our magic circle? What fraction is that? Let's go to the magic circle and look. Aren't they both root 2 over 2? Sine and cos, or cos, I should say, and sine. Exactly, chat. It's root 2 over 2. So if I asked you for the exact answer, you would have to remember that pi over 4 is at the same place as 45 degrees, or, memorize that. That gives root 2 over 2. Root 2 over 2 times 14. The 14 and the 2 will cancel to 7. 7 root 2 is my exact answer. And you now have a brief introduction to how to work with both radians and degrees, whichever one is given to you. You will need to practice the conversions of radians to degrees and degrees to radians to really start getting comfortable with this. So let's just do a quick little summary of some of the most important parts of today's lesson. So the conversions from degrees to rads, you use 1 degree is equal to pi over 180 rads. I'm not even going to put the unit rads anymore because we usually don't. Okay. From rads to degrees, you use 1 rad is equal to 180 over pi degrees. that one I'm going to put the rad there so you know that the 1 represents a radian, okay? Our magic circle, extremely important. Try to, if you can, start memorizing adding by pi over 6, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, and reducing as you go. And then adding by 45 degrees, which is pi over 4. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. And simplifying as you go. Okay. And also the arc length formula. Arc length. Actually, I'll just write it like this. Arc length is equal to r theta, where theta has to be in rads. Those 3 ideas, the conversions, the magic circle, and the arc length, are really the most important things about the lesson today. Your homework is going to talk about they use W, but it's actually omega, the angular velocity. And I'm going to get you to do a little bit of reading in your textbook to start you off before you start the homework, so you get to see those questions and you can refer to them. But that is it for today's lesson. So those 3 concepts, very, very important to practice, and you will be doing that in your homework today. So I'm going to say bye for the recording.